Good morning, everybody, or possibly good afternoon, or even good evening. Welcome to day number 3 of CPR. Today's episode is brought to you by the Greek letter sigma. That's our summation sign. And before we do anything else, first let me mention a couple things that were in the warm-up video. That one inspirational saying that involved our good friend Sigma, the summation sign, that actually translated out to be greater than average. I'll let you figure out the reasoning behind it. And also on the warm-up video, there was a bit of a proof that showed that 2 is equal to 1. And of course, that was just nonsense. And the reason was because if you look through the proof near the bottom, there's a step there where you divide both sides by x. Of course, x is equal to 0. And you're not supposed to divide through by 0. All kinds of bad things happen if you divide through by 0. Who knows, that may be how this whole COVID thing got started. Some mathematician somewhere divided by 0 when they shouldn't have. Anyway, what we really want to do today is we really want to take a look at the law of conservation of momentum assignment. Okay. I know you're probably all completely done this and you've checked over all your answers. I think answers were given for 1 to 6 and you're probably just dying to know if your number 7 was right. So what we're going to do is we're going to take a look at number 7 from the law of conservation of momentum assignment. And if you can do this one, you can probably do anything that we're going to throw at you with regards to momentum. It's a fairly challenging question, so let's take a look at it. It says 2 frogs, each with a mass of 65 grams, are sitting stationary on a 250-gram log in a pool of water. They jump off simultaneously in opposite horizontal directions from each other, one at 0.7 meters per second and the other at 0.55 meters per second. Okay. And here I have a diagram of the situation, and I've converted all the mass measurements to kilograms. Here's the log with a mass of 0.25 kilograms. Here is froggy number 1 with a mass of 0.065 kilograms, jumping off with a velocity of 0.7 meters per second. And over here is froggy number 2, also with a mass of 0.065 kilograms, jumping off the log at negative 0.55 meters per second. Of course, if this log is going in the positive direction, the other is going opposite, it's got to be negative. And of course, if you had the faster moving froggy on this side and the slower moving froggy on this side, that's fine. The question is done basically the same. We'll both get the same answer, except our answers will be opposite in sign. Okay, so let's see if we can do this. Question A says, find the velocity of the log just after the frogs jump off. Okay. Find the velocity of the log just after the frogs jump off. So first of all, hit the pause button for a second and see if you can figure out which way the log is going to be moving. And I think that the log is going to be moving in, let's see, which direction. Okay. This frog over here is developing more of a velocity than this frog. So that means this frog has to be jumping harder off the log. It has to be exerting more force on the log when it jumps off. So that means that the log is going to want to move this way. And we want to figure out, of course, just what that velocity is. So it's kind of good. We already know that when we figure out the velocity of the log, that it should be in the negative direction. And take a look at the masses involved. The log has a much bigger mass than either of the frogs, so the log is probably going to be moving much slower than either of the frogs. Okay, so let's see if we can figure this out. Now, take a look at this. What do you see? I see a bunch of masses and a bunch of velocities. Mass and velocity together, they say to me momentum. I have an explosion taking place. Things are getting blown apart. Whenever you have an explosion, things getting blown apart, or a collision, things coming together, think about the law of conservation of momentum. The total momentum of everything before is going to be equal to the total momentum of everything after. The total momentum of everything before is going to be equal to the total momentum of everything after. So PT is equal to PT prime. Once again, that prime mark denotes what's happening after our event, after our explosion has taken place. All right, so let's do this. Well, what's the total momentum of everything before? Well, remember, the two frogs are sitting motionless on a stationary log, so nothing is moving. There's no velocity whatsoever, so the total momentum of everything before is equal to 0. What's the total momentum of everything after? Well, after the explosion, the momentum is divided up into 1, 2, 3 parts. So let's add all those parts together, and there's going to be the total momentum of everything after. What's the momentum of this frog right here? It's going to be the mass times the velocity. So 0.065 times negative 0.55. What's the momentum of the log going to be? Well, mass times velocity. 0.25 times VL, which is what we're looking for. What's the momentum of our other frog over there? Well, again, mass times velocity. 0.065 times 0.7. And let's solve this now. If you multiply these two things together, okay, I believe you get negative 0.036. If you multiply these two things together, I believe you get 0.046. So solving this equation, this goes over to the other side, becomes positive. This goes over to the other side, becomes negative. Take this over to the other side, and it goes downstairs. And there's your answer. You do that arithmetic, and you get the final velocity of the log is negative 0.04 meters per second. And that answer makes sense, right? It's negative, like we thought it would be. And it's also much smaller than either of the frogs, seeing as the log is much bigger than the frogs. All right, and looking back at question A, there's a couple more things there. It says, would the log be moving at this velocity 3 seconds after the frogs jumped? Explain. Well, no. This is going to be the log's velocity right after the frogs jump off, 3 seconds after the frogs jump off. Probably water resistance and air resistance, especially water resistance, are going to slow the log right down. Okay, those are outside forces, and remember, they really mess with the law of conservation of momentum. But right after the frogs jump off, before those outside forces have a tendency to mess with things and really change with things, yeah, that's going to be the velocity of the log. Okay, let's move on to part B now, which says, what is the impulse that each frog exerts on the log? Okay, so this frog is jumping off in that direction. They're obviously exerting a force on the log for some time. You multiply them together, and there's the impulse that froggy number 1 exerts on the log. And same thing over here, right? This froggy, it jumps off in the other direction, so it's going to be exerting a force for some length of time. On the log, like so. So there's the impulse froggy number 2 exerts on the log. And we have to figure out, yeah, what this impulse is and what this impulse is. Okay, so how can we do this? Okay. Well, a lot of people are, and myself included, when I first look at this, I'm going to say, well, the impulse acting on the log, that'd be this one, plus this one, is going to be equal to the log's change in momentum. The log's mass times the log's change in velocity. Now, remember, the log is going just after the frogs jump off that fast, right? So what's the log's change in velocity going to be? It's going to be its final velocity, take away its initial velocity, which is 0 because it was stationary. Okay. All right, not so good. I got an equation here, but 2 unknowns. This is going to be pretty tough. What else can I do? Because I really don't think I can use this to figure out either of these impulses. Remember, that's the whole idea of the question. What impulse does froggy number 1 exert on the log? What impulse does froggy number 2 exert on the log? And this is not going to do it. Let's try something else. How about this? If froggy number 1 exerts a certain force on the log, that means the log is going to exert the same force back on froggy number 1, but in the opposite direction. Again, if froggy number 1 exerts a certain force for a certain time on the log, well, the log is going to exert the exact same force for the exact same time on froggy number 1. Now you got to remember, these two things are equal to each other. If this one is F delta T1, this one is the opposite of that. It's going to be negative F delta T1. And we can figure out what negative F delta T1 is. Watch this. The impulse on froggy number 1 that's the impulse on froggy number 1, right? Is going to be equal to froggy number 1's change in momentum, which is going to be its mass times its change in velocity. Its final velocity, take away its initial velocity. And remember, it was stationary at the beginning. And if you do this arithmetic, you get .046. Don't forget your units. Units of force multiplied by units of time, that's going to be Newton seconds. Now remember, we just figured out the impulse that the log exerts on froggy number 1. But we want this thing, the impulse that froggy number 1 exerts on the log. Well, take a look. These two things are opposite. So if this one is positive, well, this one is going to be negative. And you can tell just by looking at it that it's negative. It's going in the negative direction. There you go. There's the impulse that froggy number 1 exerts on the log. And we can do the same thing on the other side for froggy number 2. Right there, there's the impulse that the froggy number 2 exerts on the log. So here's the impulse that the log exerts on froggy number 2. These two things are exactly the same, except this one is going to be opposite this one. This one is going to be the negative of this one. Okay. And we can follow the same steps as we did over here. What's the impulse on froggy number 2? Well, it's going to be equal to froggy number 2's change in momentum. Its mass times its change in velocity. Final velocity, take away its initial velocity. And you do this arithmetic and you get negative 0.036 Newton seconds. Now remember, that's the impulse that the log exerts on froggy number 2. We need the opposite of that, the impulse that froggy number 2 exerts on the log. So whatever this number is, this one is going to be the opposite. This one is negative, so this one is going to be positive. And that's done. It looked kind of impossible at first, but if you remember Newton's third law, for every action force, there's an equal and opposite reaction force. It got a lot easier. Okay, let's move on to part C. Now, just before we do that, I'm going to record a couple things here. This one is equal to that. This one is equal to that. All right, now we're ready to do part C. Here comes part C. Find the total impulse that is exerted on the log. Okay? The total impulse on the log. The total impulse on the log. Well, that's easy. If you want to find a total, you just add things together. The total impulse on the log is going to be this impulse plus this impulse. and you add those two things together and you get negative 0.01 Newton seconds. Notice that it's negative, it should be negative, right? Because the log ends up going in the negative direction, so yeah, it had better feel a total negative impulse. So that was part C. Part D says calculate the velocity of the log just after the frogs jump off by using the ideal that the total impulse acting on it equals its change in momentum. Okay. So the total impulse on the log is going to equal the log's change in momentum. The log's mass times the log's change in velocity. Well, the total impulse in the log, we just figured that out. That was negative 0.01 Newton seconds. The mass of the log, 0.25. The log's change in velocity is going to be its final velocity. Whoops. I screwed that up. That's what we're trying to figure out, right? It says calculate the velocity of the log just after the frogs jump off. Okay. We're trying to figure this one out, again, a slightly different way. So the total impulse on the log is going to be equal to the mass of the log times the log's change in velocity. Its final velocity, which is what we're trying to figure out. Take away its initial velocity, which is 0 because it was stationary at the start. And if you solve this equation, can't do much with the left side. On the right side, VL take away 0 is just VL. So you take the 0.25 across the other side, it's going to go downstairs, and there is your answer. Negative 0.01 divided by 0.25, and that comes out to negative 0.04 meters per second. I'm happy to see that pop up because that's what we got the first time. Okay, there is question number 7 laid out in all its glory. Again, this is probably about as tough as you get if you're talking about the conservation of momentum in straight lines without involving any vectors. Speaking of vectors, that's what's coming next. We're going to take a look at the law of conservation of momentum as it pertains to vectors. I will post a video on that shortly. Bye for now.